DeepSeek, a Chinese AI lab, just dropped a paper saying there's a whole new way to build these models that could supercharge them. It's like discovering a secret upgrade in a game you thought you knew inside out. And it could change the whole playing field. At the heart of modern AI lies something called a residual connection. Picture it like a shortcut that lets information skip ahead in the network. This shortcut was a lifesaver that stopped training from collapsing as models got deeper. But here's the catch. It made all the data squeeze through one narrow tunnel. It kept things stable, but also limited how much information could flow around inside the model. Researchers wondered, what if we widen that tunnel with multiple streams? This idea, called hyperconnections, sounds great on paper. Instead of one path, imagine several parallel lanes mixing information. In early tests, training looks fine, but as you push the model, those unconstrained streams start to misbehave. Tiny errors get amplified layer after layer. Signals blow up, and the model literally crashes out of nowhere. It's like opening multiple faucets at once without pressure control. Suddenly the whole thing floods. DeepSeek's new idea fixes this with what they call Manifold-Constrained Hyperconnections, or MHC. Instead of a free-for-all mix, they force the blend to stay balanced. Every mixing step is designed so that each input stream shares data evenly. In math terms, each row and column of the mix matrix adds up to 1. Technically, they use the Sinkhorn-Knopp algorithm to enforce this balance. The result? Signals neither blow up nor vanish. You get the multi-stream advantage without the chaos. They put MHC through real tests. DeepSeek trained language models of 3 billion, 9 billion, and 27 billion parameters using this method and compared them to standard models. The MHC versions consistently came out ahead. For example, on a tough math reasoning benchmark, the 27B model's score jumped from about 47% to 54%. Logical reasoning tests climbed from the mid-40s to around the low 50s. Even general knowledge tasks saw healthy improvements. These aren't tiny gains. In big models, a few points can be the difference between average and top-tier performance. Now, you might think, great, more streams sounds better, but doesn't that massively slow down training? DeepSeek tackled that too. They rewrote much of the training code with custom GPU tricks, combining operations into single kernels, using a tool called tilelang, recomputing some values on the fly instead of storing everything, and overlapping data transfers with computation, a method they call dual pipe scheduling. Thanks to these optimizations, quadrupling the internal pathways only added about 6 to 7% extra training time. That's a small price for a 4x increase in internal capacity. Why is this so exciting? Because it opens a new way to scale AI. We used to think making models better was just about adding layers, more data, or bigger chips. MHC shows we can also re-architect the information flow itself. DeepSeek essentially kept the stability of the old residual shortcut, while giving the model multiple lanes to work with. Many experts are calling it a breakthrough, not just a minor tweak. It's more like a blueprint for how the next generation of models might be built. What makes this even more interesting is the timing. DeepSeek already made waves earlier this year with their R1 model, which matched frontier reasoning systems at a fraction of the cost. Analysts called it a Sputnik moment. This new paper feels like a continuation of that story. They're not just competing on performance, they're rethinking foundational assumptions. And they published this openly. Anyone can read it, experiment with it, build on it. Some analysts think this signals confidence. Others see it as strategic positioning in a rapidly evolving AI landscape. Now, you'd expect widening the internal data flow by 4 times to slow everything down, right? More streams mean more memory pressure, more GPU overhead, more training time. But DeepSeek rebuilt the entire training stack to handle this efficiently. Custom GPU kernels, selective recomputation, overlapping communication with computation. The result? Training time only increased by about 6.7%. That's a 400% increase in internal capacity for less than 7% overhead. That's insane. What makes this even more interesting is the timing. DeepSeek already made waves earlier this year with their R1 model, which matched frontier reasoning systems at a fraction of the cost. Analysts called it a Sputnik moment. This new paper feels like a continuation of that story. They're not just competing on performance, they're rethinking foundational assumptions. And they published this openly. Anyone can read it, experiment with it, build on it. Some analysts think this signals confidence. Others see it as strategic positioning in a rapidly evolving AI landscape. DeepSeek isn't new to surprising us. Remember their R1 reasoning model last year? It matched top Western AI models on reasoning tasks using far less compute. This new paper feels like its sequel. DeepSeek has rebuilt the pipeline again and thrown in some unconventional ideas. They even published the research openly, inviting the whole world to test it out. You can bet other labs are already paying attention and experimenting with these manifold constraints. So, what do you think? Could these balanced multi-stream connections be the next big leap in AI design? Or just a clever curiosity? One thing's certain. Even in a field as explored as deep learning, there are still fundamental ideas to rethink. I'm excited to see where this leads. Let me know your thoughts. Thank you for watching, and I'll catch you in the next one.